Uh, Hi, I'm Sara. I'm a postdoc at the university, as Victor said, and I'm going to talk a bit about this nested filtering framework and how I try to reduce a bit or do something about the number of particles so it gets the computational complexity is reduced a bit. This is a joint work with Joaquin Miguel, that was my PhD supervisor, and with Victor Elvira, that was my advisor when I was here. So I'll start from an introduction that includes like state space models, a bit of filtering background, and then I'll go on with this nested filtering framework that aims at estimating both parameters and states of the model. So I'll start here. Okay. The systems that we are interested in are Markov state space dynamical models that have like state that evolves with time x, that is described by a function f that depends on the previous state and a set of parameters theta, and a set of observations yt that is described by a function of the current state and also the parameters. And both the equations have some additive noise. Okay, so in terms of distributions or PDFs, we have two prior PDFs, one for the parameters and another one for the initial state. And we have also a transition PDF for the state and a conditional PDF of the observations. That's what we work with. Okay. So usually in filtering, we assume that the parameters theta are known, and all filtering methods have like a few steps that we can find every time. That it's every time a step we assume we have available the previous posterior PDF of the state conditional on the previous observations and the parameters, and we can compute the predictive distribution by using the transition. Okay, once we collect or have a new observation, we can update this distribution. We obtain the posterior, given the whole set of observations. In practice, theta is usually not known. So in order to solve this problem, we want to estimate both. So we would be interested in both the joint of the state and theta given the whole sequence of data. I didn't mention it before, but we are assuming that theta is static, not dynamic. Okay. Okay. There are a few methods in the state of the art that are quite nice that aim at estimating this joint posterior or doing Bayesian estimation for both state and parameters. We have the particle chain Monte Carlo, sequential Monte Carlo square. That's probably, at least it rings a bell at the very least. And also the nested particle filters. Okay. I think they are nice since we can quantify uncertainty. They are Bayesian methods. Also, they can be applied to quite general problems, like they can be applied to a broad class of models. And also there are some theoretical analysis or theoretical warranties that say that they converge with some conditions. Yeah. The thing is that both PMCMC and SMC square are batch techniques. That means that at some point we probably need to reprocess the whole set of observations at some point from t equal to 0 until t. And MPF, it's a bit different because it allows to be, it's basically recursive. We never need to reprocess the whole sequence, just the current observation. That's why I want to focus in this specific method. Okay. Now I wanted to explain a little bit more in detail this framework of the MPF. And then I'll explain a bit more how to implement it. So I'll show first how we apply this divide and conquer approach to estimate the joint posterior. This happens because we can split this joint into different distributions. That is the posterior of the parameters given the whole observations, and also the posterior of the state conditional on theta. The first one is the same as the one of any filtering standard filtering method, so should be a bit easier to deal with. But the key problem or difficulty is the posterior of theta given the observations. So how do we do that? As I said, theta is static, so our predictive distribution of theta is basically the posterior at the previous time step, where there is no transition for the parameters or anything. So if we want to obtain like the posterior of theta, what we would have to do is to obtain a likelihood conditional on theta, this one, in order to update the predictive. Okay, the problem is how do we obtain this? We could do it by using things that are provided by the model, and also by running filtering the filtering method for the state conditional theta. So we would have this likelihood that is provided by the model, and also the predictive of the state conditional on theta. So in order to obtain this, basically we need to run another filter just of X conditional on theta. And then with this, like we solve one thing, no, like two things with one stone. I don't know if this is expression. So we can obtain, running this inner filter, we can actually obtain the posterior distribution of the state conditional on theta, and also compute this likelihood, so we can actually obtain the posterior of theta. And then we would have the things that we need to solve the problem. Now the question is, how do we implement all this? It sounds very nice, just with the distributions like this, but we need to implement it or approximate it or see how we do this. So if I think about the simplest way to go, it would be like a naive importance sampling approximation. Okay. So I would start by initializing the set of particles for theta from the prior. Okay. Then we have this set, and for each particle of theta, we would run one filter, or one SMC in this case. I put it just to, it could be anything, but let's start with SMC, or a bootstrap particle filter that is simpler. So for each theta, I would run this filter of the state conditional on the particle. So I would first draw a set of state particles from the predictive distribution, that is mainly to take the particles from the previous time step and propagate them. And with the new observation, I would compute the normalized weights, that is proportional to the likelihood, and basically to do a sampling step, that is just taking using the normalized weights. Okay, so we get rid of the particles that have lower weights. Okay, and once we have that, we could actually compute the likelihood of theta I. Okay, using it's the sum of all of the weights we compute before in the inner filters, or the second layer. And then we could represent the posterior of theta with the normalized weights corresponding to this likelihood. That basically in the where the theta i's are placed. Okay. Okay, this has a few problems. Okay. First of all, we have to be very careful with the prior. We are just trusting the prior. And if it's not close to the posterior distribution, or is not even overlapping, what will happen after a few time steps is that all weights or most weights will go to 0, and there will be some degeneracy of the methods. Another thing we could do, we think, okay, let's, instead of taking just the prior, let's take the information we have now at the current time step, that is the posterior of theta, theta, and let's add this sampling step, and we will see if at least it's moving towards the posterior. But the problem is that when you run the inner filter for the state, we are every time we change this particle theta, we need to start from scratch. We need to run the filter from t equal to 0 to t, because it's like changing the model at the end. But in the nested particle filter, they come up with a thing that it's quite cool. That is this jittering step that allows theta to change and to explore the space. But at the same time, it says that you don't need to actually restart the filter for the state from scratch. You can just keep going on like just one step forward. You don't need to start from t equal to 0. And even doing that, you say, okay, this is going to be biased or something. It's not. It's if you describe this jittering step properly, the nested particle filter still converges to the true posterior when n tends to infinity, and then it allows to keep the method recursive, and at the same time it converges to the true posterior. And basically, this jittering, I didn't explain yet. It's like at each time step, when you want to generate new samples from theta, you draw them from this kernel, conditional on some theta prime, that it's going to be theta at the previous time step. And basically, this kernel, what it says is that with probability 1 minus epsilon n, you keep the particle like the same as it was before. And with probability epsilon n, you are going to move them with this kernel. Okay, this is important. This probability epsilon n has to be is bounded or constrained. It has to be lower than 1 over the square root of n, and the kernel can be an arbitrary Markov kernel with mean and finite variance. So an example that is valid is like just using a normal with the mean theta prime and some variance, but has to be finite. So if we apply this at the end, sorry, because this is quite dense, we get this. So what we change is this step. So we have here the jittering when we come from this kernel distribution, and we just run one step forward in the inner filters, like not from t equal to 0, but from t minus 1 to t. And then at the end, we do our sampling for the whole set. I want to point out that the resampling is like for both the particles of theta and all the particles associated to that specific theta. Okay, it's like a backpack. It goes all together. Okay. So this is the explanation for the MPF, where they use like SMC, or I explain it with bootstrap particle filter. It could be something slightly different. So they implement SMC in both layers for X and theta. But it's true that at the end, we will have a total number of particles for the state that is n theta times nx. That can be problematic if we have kind of higher dimensions. So the next works we made or we've done are related to try to reduce this a bit. So another way to go is trying to implement other type of filtering methods in the different layers. The first try was to use something very fast and easy to implement as Kalman filters for the state layer. This for Gaussian models is good, but we also implemented it using extended Kalman filters or ensemble Kalman filters for nonlinear models, and it works quite well, and it works faster. It was the main goal. And following the same idea, after that, we tried to change how to implement the parameter layer. That instead of using SMC, we tried to use some other deterministic sampling method. So the number of particles, points, samples, call it whatever, it's usually lower. So we implemented basically quadrature for the parameters layer, and we kept using like Kalman, different types of Kalman filters for the state. Okay. Nice. So now I wanted to, like, I've been just 20 minutes talking about the framework, and now I wanted to show a bit how we could go further in this trying to reduce computational cost, because I just changing types of algorithms that we can use in each layer. I don't know what else to do there. So I thought, okay, let's try another thing to keep reducing cost. So the first thing we thought about is to reduce the number of particles at some point, especially in the parameter space, because at the end, each particle in the parameter space has associated a whole filter to it. So if you can reduce or remove one or two, is going to reduce a lot the computational cost. So the idea is to, okay, when this filter is close to convergence, usually the posterior distributions get narrower and narrower, closer to a delta. So, okay, maybe we don't need that many particles or that many samples to describe this distribution. We can do well with way less. And with this idea in mind, we wanted to study this in the nested Gaussian filters. That is where we use quadrature for the theta, and some other Gaussian Kalman filters for the states. Okay, so in this case, when using quadrature, the number of points is defined as some parameter alpha to the power of the dimension of theta. And basically, as we want to change the number of particles over time, I redefine this as n theta t. And what we're going to change is basically the parameter alpha. Okay. So how do we change alpha? What can we look at to know when it is a good moment to change alpha? We come up with this statistic that is based on the likelihood of theta, that probably many of you will recognize it as something that is like the effective sample size, very similar, if not the same, but we interpret it a bit different. Usually for the ESS, let's talk about this statistic first. When it's in its minimum value, when rho is equal to 1, it means that only one of the likelihoods is different from 0. That means that if it was the ESS, this would be like showing that it has degeneracy. Okay, and when it's in its maximum value and rho is equal to n, it means that all the evaluations of the likelihood are equal. So for the ESS, that would be something good, like it's performing well. But in this case, we are assuming that when all of them are equal is because they are the filter is very close to convergence, the distribution is very narrow already, and that they are so close together that we can consider them almost like redundant somehow. So the rule that we follow to adapt alpha, it's basically to reduce alpha by 1 every time this statistic rho is very close to n, not exactly n, but very close to n, following like one threshold epsilon. Okay, depending on how epsilon is chosen, is going to be more or less restrictive, this rule, in the sense that n is going to keep a large number for a longer time if epsilon is small. And if epsilon is a bit larger, it's going to be less restrictive. It means that it will reduce n very quickly. Okay. Okay. So let's go to some numerical results. I don't have many, but I think they are quite illustrative for the Lorentz 63. So the Lorentz 63 is this nonlinear model that has this butterfly shape. It is a three-dimensional problem with three parameters to adjust. And these are the stochastic differential equations that describe it. So here, tau is like continuous time. Okay, so we discretize it with Euler-Maruyama. So we have this additive noise here, and delta is the integration step. And we assume some linear observations, but partial. We only observe the first and the third state, okay? Okay, I wanted to show this. It's from the paper of the nested Gaussian filters, where we compare a few methods for parameter estimation. In the plots, I show the normalized mean square error of theta over time, and also the normalized mean square error of the state over time. Okay, and the four algorithms that I'm showing is one of them is the nested Gaussian filter that uses quadrature for theta, extended Kalman filters for the state, and also a nested hybrid filter. That means that we keep using some bootstrap or SMC for the parameters and Kalman filters for the states. Okay. I also wanted to show how it works compared to some state augmentation methods. That basically what they are is like the simplest way to tackle the problem. That is, okay, let's assume that, okay, theta is static, but what if we treat it like another part of the state? Like we add some artificial dynamics to it, and just it's like an extended state vector, and we just go on with it. This is very fast, but it has, as far as I know, it doesn't have convergence warranty, so it you never know if it's going to work. And basically what we saw is that the nested methods work better than the state augmented filters or methods. And also for this specific model, the nested Gaussian filter was working very well. It was converging a bit faster than the nested hybrid filter, and also it's true that I haven't mentioned that for the nested hybrid filter, when we use the jittering, we have to be very careful when choosing the variance in the jittering of the kernel, because it's going to affect how fast this convergence is. Okay. And in general, well, for this experiment, we saw that but the nested Gaussian filter was performing quite faster than the hybrid one. Okay. Okay. And the last plot, I think I went a bit fast. I always have this problem, but it's okay. In this plot, we wanted to show the new adaptive method, where we change the number of particles over time. Okay. So in order to show this, we ran the nested Gaussian filter with a fixed number of samples or particles, points for theta. Okay, that is the red line. So we tried like 8, 27, 64, and we keep it fixed all over the simulation. Okay, I have to say that each point reflects like it's the average of many simulations. It's not just one single simulation. Okay, so I think it's like 50 simulation runs or something like that. And in blue, we show like the performance for this adaptive nested Gaussian, where all of them start with n theta equal to 64, all of them. And they will reduce the n over time, but using different thresholds epsilon. As I said before, if the epsilon is very small, it's more restrictive, it's going to keep the same number of points for longer. And if it's bigger, it's going to be just like, okay, it's okay. Let's keep going down, like more like faster. So in all the cases, the performance, that is average normalized mean square error of theta, that's average over time. All the performance it's better compared with the original nested Gaussian. And as you can see, when the epsilon is like in the more restrictive version, the NMSE is better, it's lower, but it's a tiny bit like more costly than the other way. And I think that's it. So to summarize this nested framework, it's quite nice because it's, first of all, it's recursive. And second, is very flexible for the different implementations. We can change different filters for each ledger or for each task. And for a further reduction of the computational complexity, we've been playing with this adaptive number of particles. And I think that many more things can be done in this sense. So yeah, that's basically it. These are the references, like nested hybrid, nested Gaussian, the adaptive number of particles, and this is the paper where the jittering was introduced. Okay, yeah, and that's it.
Thank you, Sara.